Today we're going to be focusing in on section 3.5, which is working with uniform motion applications. And essentially, this whole section is going to boil down to how are we going to use this formula right here, D equals RT. If we were to break this thing down and put some labels to what each of these variables represents, same as saying the distance is equal to the rate times time. Now, rate can be a lot of different things in this problem. It could be miles per hour, it could be kilometers per minute, feet per second, anything like that. So it's a rate that we've been given. Distance, again, miles, kilometers, meters, feet, something like that. And time could be listed in seconds, minutes, hours, anything like that. Now, going through and solving the problems we have in 3.5, the process is going to be very similar to 3.3 in the sense that we are going to be starting with a problem. We want to read through the problem multiple times, identify what is and is not important or valuable information, label those things accordingly, and then create a visual or some kind of a table to keep track of things for us. We're ultimately trying to create an equation out of the problem that we've been given. So that's primarily our end goal with doing this setup process that we're going to do. And with the uniform motion applications, I should say, a lot of these are really, really nice if we set up a table, label that table, and then fill in the known information to create equations from there. So we'll go through a process with how to do that with examples here and using this formula. But again, this setup step, making that table, labeling it, filling things in, makes these problems, at least I think, significantly less of a headache. And then once we've set up and solved our story problem in parts, it's, again, don't rush your setup process with this. A lot of people, again, will say, okay, I read the paragraph once, bam, there's an equation, bam, there's an answer. And if you can do that the correct way every single time, kudos to you. I couldn't do that when I was going through these problems. So set up and solve these things slowly and in parts. Do not try and do it all at once because there's a lot going on here. I'll give you a quick preview of we've got a couple paragraphs or a couple sentences worth of stuff in here. And if you try and rush this process, that's where errors show up. In previous quarters when I've taught this class, and this section does give people some headache from time to time as we're going through it. More often than not, when people are asking me, hey, could I get some assistance on 3.5 number, blah, 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 whatever it may be. 3/4 of the time when people are asking about that and I say, did you set up a table? Did you label anything? No. Start with that. It takes a lot of the guesswork out of what to do with these. And they go and subsequently do that, and suddenly the problem's a little bit easier to set up an equation and solve everything from there. So it's enough about our generalities because there isn't a whole lot that really can be shown or expressed just with this couple bullet points. Let's dive into a couple examples with this. And I will also mention, the last thing I'll mention before we go into these, there are lots of examples in the textbook, or at least I think there's about like 4 or 5, that utilize this method that we are going to use, the table method, the labeling, and all that to create equations. So if you're looking for any examples or additional resources to take a look at, 3.5 in the textbook. I highly recommend taking a look at that. And again, a copy of the textbook is available for you guys to download for free from our Canvas site. It's in a PDF file. So we're going to take a look at our first problem here, and then we'll jump over to the Blackboard and how we set this thing up and solve it from there. So Stan and Kyle like to ride the bike path near Stark's Pond to the beach. Kyle's speed is 7 miles per hour faster than Stan's speed. So it takes Stan 2 hours to ride to the beach, while it takes Kyle 1.5 hours for the ride. Find the speed of both bikers. Okay. So again, there's a fairly hefty amount of stuff that's going on there. A lot of numbers, a lot of values going along with these. So we need to figure out how we're going to organize this and make an equation out of it, because we're being asked to find the speed of both of them. So we're going to jump over to our Blackboard and we'll start solving or setting this thing up and solving it from there. So working with our first example. So yeah, with all of these, we are going to be using that distance equals rate times time equation. I like to think of as the DIRT equation. It's kind of another silly but easy way to remember what this thing is. So we have our general distance is equal to rate times time equation. We're going to be using that. And now we're going to set up a table to help us go through this. So when you're doing this, I would recommend give yourself extra space if you need to. Okay. So we're going to let our first column here that we have, it's going to represent our distance. And then we try and figure out, okay, what units are we working with distance? Is it feet? Is it inches? Is it kilometers? And in this instance, we're working with our distance in miles. Then we have our rate, shown up here. And last but not least, we have our time, which is in, I believe it's in hours. Yeah. For our rate, we can assume it's going to be miles per hour. So this is our initial part that we're setting this table up as with our columns, at least. So one column is going to represent distance, one's going to represent the rate, one's going to represent the time. And now we need to go and break this thing down a little bit further and work with the two bikers that we have shown up here. So we have the information for Kyle, and then we have the information for Stan. Okay. Now, I'll reread the problem, and again, just like we did with our bucket problems, we're going to start filling in parts of this table with information that we do know. So our problem states, Stan and Kyle like to ride the bike path near Stark's Pond to the beach. Kyle's speed is 7 miles per hour faster than Stan's speed, so it takes Stan 2 hours to ride to the beach, while it takes Kyle 1.5 hours to ride to the beach. Find the speed of both bikers. Okay, so now we're trying to figure out what we can put into some parts of these equations. We have been told the time for both of them. We're told it takes Stan 2 hours to ride to the beach. So Stan, time, 2 hours. While it takes Kyle 1.5 hours for the ride. So Kyle's time is going to be 1.5. Now, looking at the speed column, trying to find out, okay, how fast did each of them go? What information in the problem gives us anything related to the speed? We're told Kyle's speed is 7 miles per hour faster than Stan's speed. So we have two different values in here. And if you want to set up two equations or two things with that, you're welcome to do that as well. So I'm going to let the speed for Stan be represented by x. I don't know what that speed is going to be. And I'm going to let y, we're going to go off of I'll refine this here in a second. I'm going to let the speed of Kyle be represented by y, because it's another unknown. Now, the nice part about what's been given to us, we know something about Kyle's speed based on Stan's speed. We're told Kyle's speed is 7 miles per hour faster than Stan's. So Kyle's speed is Stan's, that x, plus 7. This is where our terminology is still going to be coming back. They're telling us 7 miles per hour faster than. So it's not exactly one of the ones that we see showing up on the English to algebra handout that we have. At least if memory serves me correctly, it's not on there. But we can get a general idea of faster than is probably going to mean we're adding to that. So we have 4 of our 6 parts with this thing figured out. And the last part that we have in here is the distance. Have we been given the distance anywhere in this problem? And unfortunately, no, we have not. So we are going to be able to leave this as distance and distance. Now, the reason we're leaving the distance for both of them as being the exact same thing is because it's implied in this problem that they are both riding the exact same path, which means that the distances that they both travel are the exact same. They might be slightly different on the time it takes them to get there and on the speed that they're getting there, but the raw distance that they are traveling is the same. So we're going to leave that unknown for the distance just as d. So now we can rewrite these things off to the side for ourselves. as equations. So I'm just going to fill in what I've been given using that general dirt equation, distance equation. So distance is equal to x plus 7 times 1.5. Distance is equal to x times 2. Okay. So we still have the issue of, okay, well, great, I've got some equations, we've got some tables set up. How can I determine what these are going to, or what our speeds are going to be? And the really nice part about rewriting things from the table into this form that we have here with the equations off to the right is we can start to notice now this equation, this quantity of x plus 7 times 1.5 is equal to the distance. Similarly, x times 2 is also equal to the distance. So if these two things are both equal to the exact same distance traveled, I can write this all as one single equation with these parts equaling each other. So we get our resulting equation to be, I'll just put it right below here. We get our equation like this. And again, the reason we are able to set these things equal to one another is because both of them are equal to the exact same distance that has been traveled. If those distances were different, we would probably have to do something else at first to be able to work through and get it down to a single equation. But we don't have to do that here. We have everything set up and ready to go for ourselves. Now we can go through and solve this thing as if it were just any other problem that we've been working with up to this point in time. So 1.5 is distributing through. And again, at this point in time, if you're going through these, you've got decimals showing up or anything like that, any computations, you can go ahead and use your calculator to do any number crunching that you need to. Again, at this point, this part of the problem should be review. Just using our tools that we've used previously, or methods, I should say. Oops. And then 10.5 divided by 0.5 is giving me 21. So now, looking at our problem and looking at what we have written in, we were told to find the speed of both bikers. Okay. So x, let's take a quick look up here. X represents the speed, the rate for Stan. So now we need to find out what is Kyle's speed. So we're going to use this equation here to tell us what that is. So we're just going to go off to the side from what we just found. So Kyle's speed is equal to Stan's plus 7. And we now know Stan's speed to be 21 miles per hour. 21 plus 7 is going to give us 28. So what is Kyle's speed? It's 28 miles per hour. And there we have our final answer. I'll zoom this out here a little bit if anyone wants to take another look at much as I can try and fit on the screen. So again, a lot of this is going through and following the correct setup steps we have with these things. If we don't set up this table, I think these problems become significantly harder to make an equation out of and solve accordingly. That's just my personal take on it. That's what I have seen be the case for a lot of people, but just my recommendation of setting this up and make this available for yourself. And again, the labeling at the top, labeling on the side, absolutely crucial. It takes all of the guesswork out of what does this mean? What does this mean? What does this mean? And kind of look at our two columns, where did they align, and then what they represent. So moving on to our second example that we have. jump us back over to our notes before we get started on that. Okay, so our notes for this one. So looking at example problem number 2. So Dwight works in Scranton, 234 miles from his farm. He wants Mose to bring him a change of business clothes after one of Jim's pranks ruined his shirt. So they meet at a restaurant between Scranton and the farm. Dwight and Mose drive 2 hours to the restaurant. Dwight's average speed is 7 miles per hour faster than Mose's average speed. Find Dwight and Mose's average speed. Okay. Any Office fans out there, hopefully might appreciate that. At least a little bit, maybe. Okay, so once again, we have a lot of stuff that's going on in here, and we want to try and organize this for ourselves so we don't have to guess at how to make any kind of an equation or how to solve this thing. So jumping back over to our Blackboard, we'll set up our equation, our table, and everything from there. So again, highly recommend when you're going through this, set up a table for yourself. We have the distance, and we're using miles. We have a rate, which we are assuming is miles per hour. Oops. Better age. There we go. We have our time, which is also in hours. I guess not also, it is in hours. And then we have the instances and the data that we have for Dwight. And then we also have Mose. And now we're going to fill in information that we know and what we need to, everything that we need to start making some equations. So I think time is one of the easy ones to start with, but it really doesn't matter which of these squares you want to start filling in from the problem. So looking at time, we've been told the problem. Dwight and Mose drove 2 hours to the restaurant. So looking at our time, we're going to have here. Did I get the wrong problem? Okay, there we go. Sorry, my screen jumped to a different part here, and I had some stuff looking incorrectly. So we've been told Dwight works in Scranton, 234 miles from his farm. So the distance that they're going to be traveling, the total distance could be 300 or 234. Now the problem that we have here, though, is that the distance that they traveled isn't going to be 234. From that, what I mean is, I'll draw a little visual down here. We have the office over here. I guess technically in Scranton, but all the same. And then we have the farm over here. Now this entire distance is 234 miles. However, in the context of the problem, we're told they meet at a restaurant between Scranton and the farm. So we don't necessarily know where it is, but we know somewhere along this distance in between them, maybe it's something like this. There's a distance that they're traveling from the farm to the office and a distance, or to the restaurant, I should say. And a distance from the office to the restaurant. And we do not know what each of these distances are. Some amount of miles and some amount of miles. So while the combined total is going to add up to be 230, could add up to be 234, if we're looking for specifically what the individual distances are, we don't know what that is going to be. So again, I want to emphasize that because a lot of people will see, well, it's 234 miles from the farm to that. And yes, it is, but we are not necessarily looking at them traveling the entire distance. They're being somewhere in between, and we don't know what that value is. So based on the information that we have, we're going to still try and fill in everything that we have from here. So based on what we've been given, Dwight and Mose drove 2 hours to the restaurant. Okay. So what is the time for them? Well, we were told Dwight and Mose drove 2 hours to the restaurant. So it's 2 hours and 2 hours. We do not know the speed that each of them traveled at, but again, we have been given information regarding that, the relationship between the two. We're told Dwight's average speed was 7 miles per hour faster than Mo's average speed. Okay, so the difference is in there. And I'm going to use x and y again for my variables, but you can choose whichever one you want. I know Dwight's average speed based on Mo's average speed. So I'm going to let Mo's be x, and I'm going to let Dwight's speed be x plus 7. So from here, we've got that. We don't necessarily know the distance that they traveled, and we know that they're going to have two completely different distances that they traveled. So from here, we have another unknown that's showing up. We have some distance that Dwight traveled, so I'm going to label that as d sub 1. Just a little subscript for our first distance. And we don't know the distance that Mose traveled. I want that to be distance sub 2. Well, again, there's a little subscript. There's nothing particularly important about it or that states any specific value. It's just there as a placeholder to show us that we have two distances is all. So as we're looking at this thing now, if it's not apparent to you with looking at it, which is fine, we're noticing, okay, don't exactly know how we're going to be able to solve this equation for having technically three unknowns in here, right? Because we have an unknown distance traveled by Dwight, an unknown distance traveled by Mose, and then these speeds that we have here. Well, I guess just an x value. So we can start to set up a couple equations out of this. We're actually going to be able to use a little bit of implications that we have here, but we can work this accordingly. So our first formula, the distance that Dwight traveled, so we have here. And then we have the distance that Mose traveled. We have that there. So at this point in time, we've got some information regarding each of the distances, each of the speeds, anything like that. But now I need to figure out how can I get all of this in terms of, maybe only solving for one of these variables or needing to only have one extra variable in here. So again, we know that the distance that they each traveled in some way, shape, or form is going to add up to being 234 miles. So we actually have another kind of hidden away formula in here. We know that, I'll put this just right below the one that we have here. We know that the distance Dwight traveled plus the distance that Mose traveled is going to add up to be 234 miles. Again, I don't necessarily know what that exact value is at this point in time, but we know that we combine each of those individual distances are going to add up to, but we know the combined total is going to be 234 miles from there. Okay. And from here, I'm actually going to move us down just below here and rewrite all of these next to one another. So it's not vertical and right into other stuff. Oops, it's just going to be x. Come on. There we go. So we've got this written in here for ourselves. So we have the distance that Dwight traveled, we have the distance that Mose traveled, and then we have what theoretically the combined total of those distances is going to be, at 234. Now we're looking at this saying, okay, well, how could I move these things around? How can I solve for what I need to get the answer to this? And we actually have written in here the ability to now do a little bit of substitution. Our first equation that we have represents the distance that Dwight traveled. Our second represents the distance that Mose traveled, and our third represents the total. So with our total consisting of the distance of Dwight plus the distance of Mose, I could rewrite d1 or d sub 1 and d sub 2 in that third equation with the equations that we just created here and here. And then I could solve for an x value and I could find my final answer from there. So that's exactly what we are going to do. So instead of having d sub 1 plus d sub 2 is equal to 234, I'm going to put the distance that Dwight traveled plus the distance that Mose traveled is equal to the total distance in between the two. So again, bring us back to our picture. We don't know the specific distances that each of them went through. Don't know that value, don't know that value. But again, I know the combined total of their distances that they traveled to be 234. So that's where we're getting that from. If we wanted to, we could rewrite this visual here just a little bit. It's an unknown number of miles still for now. We could list it as distance 1 and distance 2 if we wanted to as well. So now we've got our equation set up, we've got an equation to solve, and now we can go through and solve this mechanical problem just like we've done with previous ones in the past. So nothing special that we're doing here at this point in time. Oops. Except hopefully writing the right thing down. That would be nice. Combining like terms on the left-hand side. I'm subtracting 14 from the left-hand side and the right-hand side. And then 234 minus 14, it should be 220. And then last but not least, divide both sides by 4. I get that x is equal to, I'm doing that calculation off to the side of the calculator. I'm getting that x is equal to 55. So let's go back up and clarify for ourselves what does x represent in the context of this problem. And x represents this up here. Again, the table is great for this. So x, when it's written in here on the table, represents the rate or the speed of Mose. So now I need to find the speed of Dwight right here, because that's the thing that we're being asked to find, is that average speed. So I just need to plug in that value that I just found in for x in this equation, and then I can get my answer. Or both of my answers, I should say. So Dwight's speed was illustrated as x plus 7. We know x to be 55. And we get 62 miles per hour. So our speed of each of them, one is 55, the other is 62. And we're good to go there. So again, I want to emphasize this because I've had some people ask about this in the past, so just want to make it abundantly clear. When you are setting up these tables, you might be asking yourself, okay, well, in the first example, you set the rate to be y equals, and then add a bunch of stuff in. And the second one, you didn't do that. You just went with the equation based on the other variable that we had here. And do we have to do that for these problems? And you can choose either of these ways that you want to write it out for yourself. If you want to list a second variable and then rewrite it inside that box, you're welcome to do that. If you want to bypass that and then just go right to creating an equation like this, you're welcome to do that as well. Either option works. Okay. Let's take a look at our third example in this section, because I do think these are very much worth seeing a lot of examples on. Really hoping this thing stops lagging on me as much as it is. Okay, let's jump back to our notes and we'll take a look at our third problem that we have here. Oops. Okay, Ron and Leslie leave Pawnee City Hall at the same time. Ron drives west at a rate of 72 miles per hour, and Leslie drives east at the speed of 76 miles per hour. How long will it take them to be 330 miles apart? Okay. Any Parks and Recs fans out there? Hopefully, again, throwing a little bit of mildly amusing things in there, hopefully. Okay, so again, we want to set up, we're being asked about something with distances, or we have some rates showing up, we have some time, trying to figure out what we can and can't do with that. So let's jump back over. This is a problem we're referencing for number 3. Set up a table, let's maybe make a little visual for ourselves, and then go from there. So again, making this table. We have our distance, which is in miles, as we've been told. We have our rate and our time. Rate, miles per hour. And then our time, we're working with, looks like it's hours again. Okay. And then we have the two situations that for each of them, we have Ron, we have Leslie. So we're going to fill in the information that we do know in this problem, and then we're going to go start filling in and maybe making visuals and help us out with the rest of this. So reading the problem again, Ron and Leslie leave Pawnee City Hall at the same time. Ron drives west at a speed of 72 miles per hour, and Leslie drives east at a speed of 76 miles per hour. How long will it take them to be 330 miles apart? So filling in what we know the speed, the rate that each of them traveled. We're told Ron travels west at a speed of 72 miles per hour, so that's one of our rates. And then Leslie travels east at a speed of 76 miles per hour. Now we're asking and looking at our distance and our miles, distance in miles, and our time in hours. We do not know how far each of them has or will have traveled. So it's another instance where we could say, well, what's the distance that Ron traveled? Well, it's probably going to be some amount. And then Leslie's going to have traveled some different amount. And the time part is now going to be, it's one of these tricky ones. We're asked, how long will it take them to be 330 miles apart? So this is an instance where we are looking for the time. We don't know that, but we are assuming that because they're both moving apart from each other and then they're going to instantaneously be 330 miles apart from one another, that is going to be at the same amount of time. So I don't know how long that is, but I do know that the time that they've traveled is the exact same. They're doing it at different speeds, and it means that they have traveled different distances, but the amount of time they are Each driving is the exact same if you were to look at it on an individual basis. Now, I'm going to, right below here, make a visual of this. I think this is worth seeing as well. And you're welcome to do these when you are working through problems. I recommend them. I think these story problems, especially these ones, really lend themselves to doing that. Oops. City Hall. So let's think on the visual of this thing. We're told Ron drives west at a speed of 72 miles per hour. So traveling west, we have Ron. Traveling east, we have Leslie. Now, we do not know how far each of them traveled. So we can label this thing as the distance that we have right here, d sub 1. It's the distance that Ron traveled. Again, we don't know the specifics on it, but we know that he traveled some distance. And similarly, we know that this part over here is the distance that Leslie traveled from town hall or city hall to some distance away. We also know, based on what we're being asked, how long will it take them to be 330 miles apart, which means the distance from, I'll use gold here, from where Ron is all the way out to where Leslie is 330. So very similar to what we did with our, with our previous problem. We say, okay, well, I know the total distance, and I can break it down into each of these two smaller ones. I don't know what those values specifically are yet, but I can break them down to into its smaller pieces and solve things from there. So we are going to be using a similar process that we did with our previous one, which is we're going to break this whole 330 miles down to an equation. And then we're going to rewrite each of our parts from the table as equations as well. Because our goal with these is to make these generic mechanical math problems. So we have our two equations there coming directly from the table. And then we have our final one that's going to be coming from our picture that we have down here. And I'm going to put all three of those together all in one spot. Again, I think keeping the work organized in the sense of, okay, you might write something here and there on different parts of your paper, which is fine. But if you're trying to bring everything together as a single one equation, or bring everything after you've done all that, reorganize it all. So it's all right here in a nice organized place for you. And now, just like we did with our previous problem, we know that distance 1 plus distance 2 is going to be 330. We are given the fact that our first distance can be written as that value there, that's 72 times t. Distance 2 can be written in as 76 times t, and I can suddenly create an equation using substitution where I only have one variable that I'm solving for. Just like we have here. So distance 1, distance 1, distance 1. We have distance 2, distance 2, distance 2. And now we have just created one equation with one unknown. It's going to tell us a time, which is exactly what we are looking for. We're being asked how long will it take them to be 330 miles apart. And now we just go through and solve this thing as if we're solving any other mechanical problem in the past. So 72 plus 76, I don't know what that is off the top of my head. Apply your calculator. 148. And now we're dividing both sides by 148. And we are getting a decimal that is showing up when we do that. So I'm getting 2.22972 and a bunch of other stuff. So this problem did not specify where we're going to be rounding this thing. So for the instance of this, and again, this won't be shown up on the test. I will be like this on the test from the standpoint of where we round it to. I will be specifying for you guys where to round your answers to. So for the sake of it, let's round this thing to 1 decimal place. So our approximate time is going to take them 2.2 hours to be that far apart. And we have our final answer. So again, I think these problems are very, very, very helpful if we keep our work organized and we make these silly little visuals for ourselves. But again, I recommend making these tables, labeling these columns so you know exactly what each part of them represents. I think it's very helpful. Made life a lot easier for me when I finally learned how to do this and actually started doing it, because I struggled with these problems back when I was learning this as well. So this is pretty much everything that we have for the 3.5 material. This is our uniform motion application problems. So be willing to make this table for yourself, be willing to maybe do and make a couple drawings for yourself. Again, as you guys can see, I'm not an artist. So we're seeing right here. Taking a look at our other problem that we had. I'm not an artist here as well. I'm not grading you guys on being artists in this class, but making that silly little visual so you know what these things may or may not represent, I think is extraordinarily helpful with going through and solving these types of problems. So don't discourage or don't discount making the visual, and absolutely do not discount making this table for yourself. This is really, really helpful, I think, as we go through these. But that is everything for 3.5. I'm going to end the recording here, and we'll take a couple questions and then move on from there.